Hello everyone, welcome to this video. In this video, I am going to explain the module 1 in basic electronics and communication engineering, that is electronic circuits. In that, the first chapter, power supplies. So to this particular module, we are going to refer to chapter 6 in this particular book, Electronic Circuits, Fundamentals and Applications, written by Mike Tooley. This is the 4th edition and the Elsevier publication. Refer this book for this particular topic. The chapter 6 covers the power supplies. So in this video, I am going to cover the block diagram of DC power supply, half wave rectifier and a full wave rectifier. Block diagram of a DC power supply is as shown in the figure. In this block diagram, you can observe a high voltage AC is given as input here, and finally we are going to get with a regulated DC output. The block diagram of the DC power supply, here it is shown, means we are going to get the regulated DC output by giving the high voltage AC. Once we given the AC voltage to the step down transformer, we are going to get a low voltage AC as output of the step down transformer. And that is an input for the rectifier. Rectifier is going to convert an AC signal into DC. But the output of the rectifier will be unsmoothed DC signal. To smooth that signal, we need to have a smoothing filter and a reservoir circuit. And then the output of that will be smoothed DC, and that will be given to the regulator to get the regulated DC output. Now let us see the blocks one by one. First, we will be having a step down transformer. The step down transformer is that it will be having two coils wounded to a iron core. One will be called as a primary coil, to which we are going to provide the high voltage. And the secondary coil will be having less number of turns compared to primary coil, and the output will be taken at the secondary coil. And here you can observe the high voltage AC is converted into a low voltage AC here. The step down transformer is going to reduce the amount of voltage. And next we will be having a rectifier. Rectifier is a device that is going to convert AC into pulsating DC. So in the figure, you can observe here in the waveform, the AC voltage which is coming out of the transformer is like this, and it is removed the negative half cycles, only the positive half cycle of the output we are going to get as output of the rectifier. But here you can observe it will be consisting of an AC component. Means that is what the unsmoothed DC we can say. So we are going to give this signal to an reservoir or smoothing filter circuit. This reservoir, what it is going to do? Reservoir will be having a capacitor circuit, and smoothing filter again will be having within the device. It is going to smooth the signal by removing the ripples. You can observe here, this is what the filtered output we are going to get as output of this particular block. And that will be called as a smoothed DC signal. And that will be given to the voltage regulator. Voltage regulator will be having an active component like transistor and a diode arrangement. Zener diode will be generally used. And we are going to get a DC output like this, steady output like this. That will be called as a regulated DC output. Here the regulated DC output, in the sense, even if there is a small variation in the input of the voltage regulator, it will regulate the DC output, and we are going to expect a constant output from the voltage regulator. This is what the block diagram of the DC power supply. Here you can observe the components like step down transformer. It is having a coil, and in place of rectifier you can observe here this is a bridge rectifier arrangement, and then reservoir and smoothing filter we can have a capacitor like this, and voltage regulator we will be having a Zener diode as well as the transistor arrangement. These are all the principal components present in these particular blocks, we can say. So the real-time example of a DC power supply device, it will be like this. This is, you can observe here there is a transformer, a step down transformer. The input of the transformer will be an AC input, and it is going to give the output from the secondary. We will be having a bridge rectifier circuit here to convert that AC into pulsating DC, and we need to smooth that signal. That's why we'll be having a reservoir capacitor here. You can observe here, this is a capacitor, and we are going to get an output from the regulator, that is the DC output, right? And to for the safety purpose, we will be having fuse at the primary of the transformer as well as the secondary of the transformer. So this is the available DC power supply device in the market.
दोस्तों, क्या आपके MS ऑफिस सॉफ्टवेयर के अंदर ये वाला ऑप्शन है? ध्यान से देखो, इसे कहते हैं को-पायलट।
And here we need to understand rectifier is the one of the main component in DC power supply. While converting an high AC into DC, we need to have a rectifier. So the definition says rectifier is a circuit which converts AC signal into pulsating DC. So here we need to understand AC signal to pulsating DC means the DC signal coming out of the rectifier will be having AC component that will be called as pulsating. And here generally we are going to use semiconductor diodes to convert the alternating current, or we say alternating signal, to direct current or the direct signal. And you can observe here the semiconductor diode, how actually it will be. It will be there in rectifiers. This is what the symbol of the diode. It is a triangular symbol with a dashed line like this. This end will be called as anode and this end will be called as cathode. It will be having a PN junction. P region as well as N regions are connected together and it is forming a junction in between. And this is what the component of the diode which is available in the market. It looks like this. And this end is anode, and here you can observe a silver line indication of cathode, that is negative. And how this diode is going to function? If we connect the diode to a positive power supply and other end of the diode is connected to the negative power supply, then we say it is forward biased and diode is going to conduct. The current flow in the diode will be in this direction, and diode will allow the current to flow in only one direction. And when it is reverse biased, means negative power supply is connected to the diode anode and the positive terminal will be connected to the cathode, diode will be reverse biased and there is no amount of current flow in reverse direction. That's why we say when the diode is in forward biased, it will be conducted. When it is in reverse bias, it is not going to conduct. And how this diode is going to work? When we connect an AC signal like this, see now the positive half cycle of the input is giving to the diode and diode will be forward biased and conducts. When it is negative half cycle, diode becomes reverse biased and it will not gives any output. Zero will be the output when the negative half cycle of the input coming to the diode. And as the positive half cycle of the input comes, diode will conduct. That's why we are getting the same kind of output here as it is in the input side. Next we have rectifier circuits. By using this diode functionality, we can have different kind of rectifiers to convert an AC signal into DC signal. The first one is half wave rectifier. What is half wave rectifier? Half wave rectifier is a device. It is going to convert an AC into pulsating DC, but the output of the half wave rectifier will be half cycles if we compare to the signal at the input. So let us understand what is half wave rectifier. So in this circuit, you are seeing a simple half wave rectifier circuit, which the input will be 240 volts AC signal. Here you can observe this is an AC signal we are connecting as input to the transformer primary coil. And at the secondary coil we are going to get equivalent 12 volts, means this is a step down transformer. It is reducing the voltage from 240 to 12 volts. And we are connecting that to the diode D1. And this, as we know, diode D1 conducts when it is forward biased and diode D1 is off or it will be not conducting when it is reverse biased. So we will be having a load here, that is RL. We need to observe the voltage across RL so that we can observe the voltage generating from the rectifier. So to understand this, we need to look at the input we are giving and what actually the output it is going to give. This is the AC signal we are giving, the large AC signal, and it is converting into pulsating DC like this. At the positive half cycle of the input, we are going to get the output as it is with the reduced voltage, and in the negative half cycle of the input, diode will not conduct and output will be 0. And here is the explanation for that. When the positive half cycle of the input is connected, given diode D1 conducts, that's why the switch is closed here. This will make the path to current flow, the current flow will be in this direction, right? So across RL we are going to get the output like this. When it is reverse biased, means the negative half cycle of the input is given. What happens? Diode becomes reverse biased. Diode reverse biased means diode will be off. So the switch is open. There is no connection between this end to this end. So there is no current flow. When there is no current flow, there is no output across RL. That's why here in the previous slide we seen the output will be only half cycle. The negative half cycle of the input comes, there is no output here. Here is the waveform that gives the meaning to this particular operation of half-wave rectifier. Here the blue wave indicating an input signal and the red line indicating an output signal. You can clearly observe in the positive half cycle we are going to get the output, and in the negative half cycle there is no output generated. This is the output of the half-wave rectifier. We can plot like this. And in the DC power supply we have seen, after the rectifier we will be having a reservoir and the smoothing circuit. This is what the reservoir and smoothing reservoir circuit, half-wave rectifier connected with a capacitor filter. This is the extra capacitor we have connected here. Once we connect this capacitor, what happens? It is going to smooth, or it is going to reduce the pulses in the output of the half-wave rectifier. Means we say ripples present in the output that can be eliminated. You can observe here the T1 secondary voltage is this, peak to peak it is plus 17 and minus 17, and voltage across RL without C1, without C1 in the sense without connecting this capacitor, this will be the output. And by connecting C1, what happens? This capacitor is going to be charged initially, up to here it is going to be charged, and when the voltage reduces, when the voltage reduces, what happens? Capacitor will hold the charge until the next positive value comes, and it start discharging as time goes. By that time it is getting the next positive value. So again it is going to be charged to the next peak value. The process continues. So what we are going to get advantage here, the ripples present over here is going to be eliminated and the curve becomes smoother. This is how we can reduce the amount of AC component present in the half-wave rectifier output by connecting a capacitor like this. This capacitor will be charged, and then it is holding its state, and as time goes it is discharging its value. By that time it is getting the next peak value, and again it is going to be charged. So this is how we can smoothen the output of the half-wave rectifier by connecting a capacitor. And here is the another circuit by connecting RC smoothing filter. Here is the filter arrangement. You can observe this R1 and C1 is the filter circuit which we have connected extra with this capacitor, reservoir capacitor. Here what is the advantage? Here the advantage is that it is going to reduce the ripples again. This makes the circuit output smoother. Here R1 C1 is act as a filter which will remove the ripples, and the value of C1 we need to choose carefully so that the component exhibits a negligible reactance, at the ripple frequency of 50 Hz for a half wave rectifier and 100 Hz for a full wave rectifier, which we have full wave rectifier we are going to discuss later. And the effect of this R1 and C1, the effect of this R1 and C1 in the sense, this arrangement, filter arrangement, it will be act as a voltage divider. Okay, and the amount of ripple reduced by an factor across this capacitor, if we observe what actually the amount of ripple voltage reduced, can be calculated by this expression XC. XC is the reactance of the capacitor divided by root of R square plus XC square. So here XC is the reactance will be 1 divided by 2 pi FC. F is the frequency of the signal and C is the value of the capacitance. And next we have full wave rectifier. As we know, the half wave rectifier is giving the output pulsating DC, but it will conduct only at the positive half cycle of the input. That's why we are going to get only half cycle output. And at the negative half cycle of the input, we are not going to get the output in half wave rectifier. That will be eliminated by the full wave rectifier circuit. In full wave rectifier, we are going to get the full positive cycle output even in the negative cycle of the input. That we need to understand here. So basically we will be having two types of full wave rectifiers. One is biphase type. It will be called as center tapped full wave rectifier. And also we will be having bridge type rectifier. So we'll see one by one now. First we will be having a center tapped full wave rectifier. So the center tapped full wave rectifier, in the arrangement itself you can observe it will be having a transformer. The primary coil will be connected with an AC signal, and at the secondary coil we are tapping the secondary coil and taking an signal here, and the secondary coil will be connected to another end of the load, and another end of the coil will be connected to the load RL. You can observe here the output of this particular rectifier is taken across RL here, across these two ends. It is from one end of the coil and with the center tapped arrangement. And two diodes are used here, D1 as well as D2, and this makes the center tapped full wave rectifier arrangement. Here also we are going to give a 240 volts of AC signal, and the available voltage at the two ends from AB and also to B to C is 12 volts RMS value. 12 volts RMS value, which is equivalent to 17 volts AC signal. So let us see how actually this center tapped full wave rectifier is going to work.
400 ml 7-Up now at 20 rupees only. 7-Up Super Duper Refresher.
Here we will be having two diodes. Let us call it as D1 and D2. When the positive half cycle of the input is given to the primary coil of the transformer, it is a positive half cycle of the input. It is making the diode D1 forward biased and D2 reverse biased. Because of the center tap here, the diode D1 will treat that as a positive signal and D2 will be treating that as a negative signal because of the positive and negative arrangement you can observe here. So D1 becomes forward biased and D1 conducts. D1 is conducting and the current will be flowing in this direction through RL and it will coming back to the negative terminal here. And because of the forward biasing, diode conducts the current flowing through the RL in this direction. The voltage across RL, if we measure like this, it is same as the input signal what we have given. Similarly, when the negative half cycle of the input is given, negative signal will be having the value negative with respect to the origin is concerned. Here it will be treated as the forward biased voltage to the diode D2. Diode D2 will be treating that as a positive voltage. Diode D2 conducts and D1 will be off. D1 will be off because it is reverse biased. So D2 conducts. Because of D2, the current will flow in this direction and it will make a path like this and it will flow through RL and it is come back to the negative terminal of the center tap. So again, you can observe here the current flowing through RL will be in the same direction. So if you measure the voltage across these two ends, current flow will be in this direction, again the voltage will be in the positive half cycle. You can observe here the voltage here it is generated is also same as the negative half cycle input. The voltage will be in the positive value. So the full wave rectifier is going to generate the signal as DC with this kind of output. Here even in the negative half cycle we are going to get the positive output. Now let us understand how actually this center tapped full wave rectifier will work. For a positive half cycle, the diode D1 conducts and D2 is off. So the positive half cycle of the input comes, D1 will allow the current to flow through, that current will flow through RL and output will be generated like this. Okay. Similarly, let us understand the negative half cycle of the input. When the negative half cycle of the input is given, it will be treated as a positive voltage for D2 and D1 becomes reverse biased. That's why D1 will not conduct, only D2 conducts, and again the current flow through RL is in the same direction. Here the circuit is modified to make it understand better. So you can observe the current flowing through RL in the same direction as the current flow through the RL in positive half cycle of the input given. That's why we are going to get the same peak value like this even in the negative half cycle of the input. This is what the advantage in the full wave rectifier. We are going to get one more signal here in the negative half cycle also, so that we are going to get a better DC output. This is what the output of a full wave rectifier for an AC signal. And again we can connect a reservoir circuit and smoothing circuit for the full wave rectifier as we connected in half wave. This C1 will be acting as a reservoir capacitor. This is what the secondary coil voltage 17 volts, and at the output of this RL without C1 we are going to get the signal like this. Okay, and it will be consisting of more AC component compared to the half wave rectifier output. So we need to reduce this AC component and we need to get the DC voltage something like this, a steady output. So to reduce this AC component, what we are going to do, we are going to connect this extra capacitor C1. What this capacitor is going to do, when the current is started to flow in this direction, even in the positive half cycle of the input and the negative cycle of the input, the capacitor will charge to its peak value. So capacitor will be charged to this value and it will be holding its value. And when the next positive edge comes, again it will be charging to that particular value. And meanwhile it is started discharging, but by that time again the next value of the peak signal comes to the capacitor, again it is going to be charged. Compared to the half wave rectifier, here the voltage getting to the capacitor C1 is more sooner than the half wave rectifier. That's why here in the full wave rectifier we will be having less more steady output compared to the half wave rectifier. This is what we are calling it as a ripple. The amount of ripple voltage is this much. Okay, so to reduce this, again we can reduce the amount of ripple voltage here. That's why we can connect one more capacitor and resistor arrangement as a filter circuit. That as we discussed in the half wave rectifier, the same kind of arrangement we can make here also. This is an full wave rectifier circuit. So next we will be having a bridge rectifier circuit. Bridge rectifier is again a full wave rectifier. It is working same as a full wave rectifier, but we can have a bridge kind of arrangement of diodes to get the pulsating DC output. It will be called as a bridge rectifier circuit. It will be consisting of 4 diodes which is connected in a bridge fashion. So the diode arrangement will be like this. If we connect this diode like this, and it will be like opposite pair of diodes conduct when the alternating half cycles are coming into an input. Means this diode and this diode will conduct once, and in the negative half cycle or the second half cycle, this diode and this diode will be conducting. The arrangement will be like that. Now let us see how actually this bridge circuit will work.
ರವಿ ಅವರೇ, ಮತ್ತೆ ಮೂಗ್ ಬಂದ? ಸುರಸುರ ಅಲ್ಲ, ಆರ್ಡರ್ ಮಾಡಿ.
ಹೇಗೆ? ಎಷ್ಟು?
ಹೀಗೆ ಬರೀ ಒಂದೇ ಸ್ಪ್ರೇ. ಆರ್ಟ್ರಿವಿನ್ ಅಡ್ವಾನ್ಸ್ 25 ಸೆಕೆಂಡ್ ಅಲ್ಲಿ ಬಂದಾಗಿರೋ ಮೂಗನ್ನ ಸರಿ ಮಾಡುತ್ತೆ. ಆರ್ಟ್ರಿವಿನ್ ಸಿಂಪಲ್ ಆಗಿದೆ.
ಬಸ್ ಬಂದೇ ಬಿಡ್ತು.
ಅಯ್ಯೋ ಬೇಡ ಕಣೋ, ಈ ಬಸ್ಸಲ್ಲಿ ಉಸಿರಾಡಕ್ಕೂ ಜಾಗ ಇಲ್ಲ.
ಲೈಫ್ ನಲ್ಲಿ ಟೂ ಮಚ್ ಆದಾಗ ನೆಸ್ಕೆಫೆ ಕೆಫೆ ಸ್ಟೈಲ್ ಕೋಲ್ಡ್ ಕಾಫಿ ಆಗ್ಲಿ, ಈ ತಾಜಾ ಗಾಳಿಯಲ್ಲಿ ಹೋಗುವ ಮಜಾನೇ ಬೇರೆ.
So again, there will be a transformer at the input. It will be having a primary coil connected to a 240 volt AC, and there is a secondary coil. Secondary coil will be giving the step down voltage, something like 12 volts RMS, and it is connected to the diode arrangement. Here 4 diodes are connected in this fashion. You need to remember how the diodes are connected, and they are named as D1, D2, D3, D4 as opposite diodes conducting at that particular time. So at the two ends of this bridge arrangement, we will be having a load RL, and current will always flow in this direction through the load. So we are going to measure the voltage across this RL. Okay. In the positive half cycle, what happens? When the positive half cycle of the input is given to the rectifier, D1 and D2 conducts. This D1 becomes forward biased and D2 becomes forward biased. The current will flow in this direction. Okay. So you can observe here, this is what the path it is going to take to reach the P point when it is the positive half cycle of the input is given. And what about D3 and D4? They are reverse biased and there is no conduction in D4 and D3. And the negative half cycle of the input, is given, what happens? D4 and D3 becomes forward biased. So the current direction will be like this. The current will flow through D3 and again through RL, it will through D4, it will reaches the other point. This is how the bridge rectifier is going to work, and the direction of current will be same in this direction. Okay, so let us understand the working. Here you can observe when the positive half cycle of the input is given, D1, D2 are connected, means D1 and D2 are forward biased and making the circuit closed switch, acting as a closed switch. And the current direction will be shown here through D1 and then through RL, and then it will flow through D2 and it is completing the circuit. And current flowing through RL is in this direction. The output can be measured across RL and output will be again in this manner. When the negative half cycle of the input is applied, the current flow will be in other direction. D1 and D2 becomes reverse biased and D3 and D4 becomes forward biased. So the current flow will be in this direction through this path through D3. Since D3 is forward biased, it will make the path to current flow through RL. Again it will go through D4 and it will reach us the other point. Here also the current flow direction will be in the same manner, in the same direction. That's why again we are going to get the same kind of output as